Okay, welcome to week 6 of computer security. In this week, we are going to study about software vulnerabilities in general. Just a second, this is the second slide. Let me check. Yes. So we will start with this one, then we will go to buffer overflow afterwards. Yeah, we will start with software security in general. So let's define the software security flows. The first of all, we should tell that the critical web application security flows include 5 related to insecure software code. So these are related to each other, and these are the insecure software practices. Like, what is this? The first one and the most important one is unvalidated input. So if for those who are taking the secure software development course, this week we have told a lot about unvalidated input and what input actually means. And I believe it's not always what you think. And so the input, unvalidated input, is the first cause of every insecure software code. Then secondly, chained by this unvalidated input, the cross-site scripting, buffer overflows, injection flows, and improper error handling could be listed as the rest of these insecure software code. So these flows occur as a consequence of insufficient checking and validation of data and error codes in programs. So what do we mean by checking and validation? You see, these are some separate words. So if they are separate words, they should have different functions and meanings. So whenever you look at a sentence like this, if those meanings are separated from each other, then they are important. So the first one is insufficient checking. We have some kinds of checking mechanism, but this mechanism can be overcome. Okay, so it can be circumvented. And validation of data and error codes. So validation has also 2 legs. One about the data, okay, data validation. And the second thing is the error codes, or as exception handling. So all of these actual flows are in, okay, according to this, these are the top errors in 2011. But even this year, okay, the latest version of top 10 of OWASP, not CV Sans, but OWASP 1 is 2025. So you can see that lots of these are still in the list. Okay, I will show that list as well. So awareness of these issues is a critical step in writing more secure software program. Yes, that's the heart of secure software development. And emphasis should be placed on the need for software developers to address these known areas of concern. So what do we do to reduce the software vulnerabilities? That report at that time, this is still valid. It recommends stopping vulnerabilities before they occur by using improved methods for specifying and building software, and finding vulnerabilities before they can be exploited by using better and more efficient testing techniques. and reducing the impact of vulnerabilities by building more resilient architectures. So on the software security, quality, and reliability, most of these flows actually are related with software quality and reliability and security together. So if the software quality is not properly applied, it will definitely lead to software security vulnerabilities. But even that is the case. So this is cat and mouse chase game. So the software developers at one time try to apply all the quality and reliability principles. On the other hand, the cyber criminals is going to attack and try to breach those systems. But most of all, the unanticipated input or unchecked input is the very first source of all software related, security related incidents compared to other ones. So that brings us the definition of defensive programming. And probably I'm going to update these slides next year, but still this year, we don't. I will not go into details of wipe coding or AI-based code generation stuff for this year, but I can tell a little bit about it while the topic agrees with that. So right now, the AI-based coding tools are very at the beginning of defensive programming. They usually suggest wrong, I would say, they would suggest wrong definitions or wrong practices of AI-based programming, and they also may generate or create code that seems to be secure. So this is the most important one. So it seems to be secure, and it says, yes, this code is secure. It says it doesn't see anything wrong with the code, but the code is actually very flawed. Okay, so that's that's what we are going to see in the near future. So AI-based programming is going to be attacked in every angle, and with this every angle, the first company that is going to be devastated, that is going to be maybe bankrupt because of AI-based programmers' security flaws, that will be a great lesson. But for now, what we need to talk about is that we definitely know you cannot give all of your steering wheel to AI. So that means, of course, you can use AI to generate code that could be more or less harmless, okay, not system-wide critical, or UI generation, some sort of stuff. But you cannot expect AI to solve every problem about security or personal information related issues, personally identifiable information, or more speaking. So PII. So these kinds of things are not right now in the eyes of the programmers, but they're going to see what will happen next year. So this is normal secure programming. With this style, I'm not going to go into details of everything because you already know the interactions between each units should be secured. That's what this is telling us about. So in this kind of defensive programming, it may conflict with the business pressures to keep development times as short as possible to maximize market advantage. You see, right now, think about it. The latest update of these slides are in, I believe, 2018. So it's nearly 8 years ago, but it is still valid in every angle. That, of course, it's always valid. It doesn't matter whether it's 8 years old. But what we can see here is that the time to market pushing of the software ideas and everything is now going to create another market for AI-based security flows. And even right now, I see some startups who claim that they are going to fix the security flows in their AI-based program generators. And even right now, the cloud company Anthropic, the company behind Cloud, has also published another use case of cloud as cloud security, so which is actually analyzing the source code and suggest improvements for the security. So we used to call these previously like static analysis of the code. There were static analysis tools, and these tools used to run and create results, and we were saying, wow, this is very interesting and some. But whenever the AI revolution started, we immediately understand that this is definitely going to change everything. In my experience here, saying that these code generations is going to hit a wall with the security related issues. But another one is going to claim that they also solve the security of the code generators right from the start. So this actually comes from the fact that the security is done by design. It's not something add-on. At that time, there was these time to market issues actually prevented the security by design to be incorporated in the code from the beginning, from the planning. But let's say from the time that this book was written to up to, let's say, last year, let's say up to last year, we had only the problem about time to market with the security design. We didn't consider the AI generated code or wipe coding at this time. So when AI generated code started, right now, these types of secure by design principles has been eliminated, and people go only with this. Okay, without taking all the controls about the security design, this will be a disaster, I believe. So this brings us how to handle the program input. Incorrect handling is a very common failing, as we know. So input is any source of data from outside and whose value is not explicitly known by the programmer when the code was written. And this is called, of course, we have three, let's say, classes of input. We just talked about it yesterday. So the first one is trusted input. Second one is semi-trusted input. And third one is semi-trusted, untrusted input. So what are the difference between those types of inputs? So the trusted input is generated by inside our code, okay? So trusted input is what the input we generate in our code and pass it to another, let's say, another programming fragment, module, or API, microservice, whatever we have in control. So this is trusted input. Semi-trusted input is the code, is the input we actually generate, and we actually, by generating these inputs, we actually send to a display, okay, like web UI or mobile UI, and we assume that whatever we generate as the input, some of the components of this input can be viewed, but we assume that these shouldn't change. Okay, these shouldn't have, let's say, some some external modifications on this input. But for the web pages, for example, if you open the JavaScript console and everything, you can change all the objects inside a web app, and your input, your weighting, your expected input can be changed. So that's why it's called semi-trusted. So you should, it's the code that you generate, but you should not trust them. You should not treat them as trusted input. And the last one is untrusted input. As usual, all the input that is physically entered by a human or a computer, which is an API style input, these are the inputs that should not be trusted in any case. So these are the untrusted inputs. So input size is the most critical component, which is going to create the buffer overflow style of problems. So the input size, why the input size matters? Because not all programs expect the same size of input. The input size should be limited according to the needs of the program, right? So you cannot expect an unlimited size of input. Every communication should have a defined size, right? Should have some particular size. So this size requirement actually creates one of the most still head-aching problem about this input buffer overflow, because in programming languages that are manually memory managed, like C and C++, you have to allocate buffers for these inputs. So if this buffer allocation is calculated, if there's a problem with this buffer allocation, this is going to create a problem that we call memory corruption, which we will see in the next phase of this session as the buffer overflow problems. So this means that this input, whenever you receive an input to your program, whether this input is an untrusted or semi-trusted input, they should always be checked properly. And still, the problems that was disclosed, by the way, Apple officially patched some new vulnerabilities, but didn't disclose anything about the CVE related with this in Safari buffer overflow, input overflow problems in the current version of updates of iOS. So, which means that still the buffer overflow problems still continue. So the interpretation of the program input could be binary or text, doesn't matter. And there was a very known, famous buffer overflow error called Heartbleed OpenSSL bug. This is, yeah, at that time of writing, it was a recent example. But the problem actually caused, this problem was caused by binary input value without checking the validity of the size, which create a buffer overflow. And with this buffer overflow, it was possible to copy the memory contents of the running server to you just in few seconds, okay? So in this memory, this is the running memory of the computer. In this memory, if this computer is running a HTTPS, okay, with certificates and everything, including if this server is running the certificate of this particular machine in the OpenSSL, the private keys of this HTTP server running could be retrieved. So this means that anybody can mimic this server's certificate. So with this Heartbleed bug, that's why most of the servers, after patching everything, had to update their SSL certificates, which is actually the HTTPS certificates. So these SSL certificates have to be updated, renewed right after this Heartbleed bug, because these certificates could be retrieved, the private keys, with this bug. Okay, this was the most concerning bug of all the time. And it was very simple. It could be just launched by a simple script. And the injection attacks are the attacks that we talk about them as to change the input data. So again, actually, I have updated the slides for the previous year's secure software development exactly at this topic. And we have talked about those a lot, but I can also share that slides with you. But the injection attacks, we have several different injection attacks, like the JavaScript injection attacks, SQL injection attacks, what we are going to see. So again, these slides have been little outdated. That's why it says most often occurs in scripting languages. So those scripting languages, particularly PHP, was most of the time vulnerable to SQL injection attacks, because the SQL handling in PHP was done with string concatenation, not the parameter binding, secure parameter binding features. So with that one, we actually have those kinds of attacks. So yeah, these are the examples for PHP style SQL injection attacks. But as I told you, I'm going to share those slides as well about the SQL style injection attacks. And the cross-site scripting or XSS style attacks are the attacks where one user, where input provided by one user is subsequently output to another user. Okay, so cross-site scripting means I am crossing the boundary of two websites. Okay, which is two websites. One website is the actual website that I want to attack, which actually is doing something useful, okay? And people do some transactions with this website. And the second website is my website, okay? Somehow I go in the middle, I go inject something on my code, and people think that this code is actually coming from this website, okay? Some of the users. So this is called the cross-site scripting. So I am behaving like I'm trying to steal the context of this legitimate website, or yeah, let's call the legitimate website, and this is the evil twin. So I am the evil twin website that steals this information. So this is basically the cross-site scripting, as we can see. And this vulnerability involves the inclusion of a script code in the HTML content. And script code may be needed to access data associated with another page. And browsers normally impose security checks and restrict data access to pages originating from the same website. So this is called same origin policy. And exploit assumption that all content from website is equally trusted hence permitted to interact with the content from the other side. Okay, so actually you have provided a bad, let's say, a script to this website, and this website, with the context of this website, it is trusting everything as a trusted script. That's how you do. So usually this happens with online advertisement websites because they have scripts running inside, and those kinds of cross-site scripting attacks usually start by injecting from the advertisement box, and so that's how they do it. So yes, this actually comes from the fact that the input syntax should be validated, and it's necessary to ensure that data conform with any assumptions made about the data before subsequent use. So you can assume that the data could be generated by me. So most of the attacks that we see are coming from the semi-trusted input, right? So never forget about the semi-trusted input, because semi-trusted input is the input actually we generate and we think that it won't change. We treat them as trusted input, but actually they are semi-trusted input. And input data should be compared against what is wanted. This means that we can do two things: either make a blacklist or deny list, or allow list. So currently, the trend is to go with the allow list of the input instead of deny list, because the deny list style of input, you could have an endless list of denies. Okay, if you think that, I mean, deny list was easier to implement at that time, they thought, but this is not the case. So we should go with the allow list of the input. Why? Because most of the time these inputs are not always the final destination, not always reaches the final destination. So for you, that input could be something, just something to be checked, and your module did not see anything wrong with this input, and this input is passed to the underlying, let's say, another program or another module. But with this module, some special syntax inside this input could mean something special to this the other program, okay, to this program. So your program, according to your program, this input could be valid, but this program right now then assumes and treats your input as a fully trusted input to there, because it's generated by you. Okay, so that means this program shouldn't again trust this input as a semi-trusted input, then apply its own rules. I mean, most of the buffer overflow and input related issues, what we see is that there is a chain of input going down the stream, and everybody implements these input filters at one stage, but one of the steps doesn't implement this input filtering, and that's where the program actually has the exploit. Okay, so if you think about the modern source code of mobile applications like Apple Safari and even Chrome, you can think that there could be endless number of input related chains inside the program that is running. Okay, so it seems that it will never end until we go to the last phase of this. So the alternate encodings actually allows you to change these inputs that could be interpreted incorrectly to some values that we believe that they don't mix up together. So this actually, yeah, in that one I've told, this actually comes from the fact that the ASCII character set was only at the first one, what had only 127 characters. Okay, then it was extended to 256 characters, okay, or 255 characters. So they try to implement everything, every type of special meanings of the characters in this limited space. So this created a backwards problem with these C and C++ developed modules. They used to could only handle these limited character set. So most of their rules and everything, previous implementation on everything, was built over the top of these limited character set. That's why their inputs were I mean, the meaning, the interpretation of these inputs could be easier if, even from the beginning of this ASCII character set, if it was possible to extend these ASCIIs as UTF, okay, then maybe these kinds of input problems we wouldn't see. But anyhow, it happened, and of course, switching to UTF-8 characters helped a little bit in some cases, but this time these characters should be handled properly, and they should be converted into encoding formats in order to pass them to other formats, because we still have dependency over the previous architectures, because our modern world is still built upon these limited sets, and that's why we still leave these together. And validating the numeric input also has a significant point in integer overflow. This is a little bit different than the buffer overflow, but the integer overflow usually creates, again, it could create memory corruptions and everything at one hand, and on the other hand, it creates calculation and even financial loss based on what we do. So another thing is that still the cybersecurity research, with the help of AI right now they are using AI as a hammer for fuzzing. Fuzzing is the most important software testing strategy for these inputs, okay, for these input style ones. So the software fuzzing actually tries to explore the input space, okay. So all of the inputs, which is infinite, it explores these inputs space for the programs to feed with these inputs and try to crash your program. So if your program is crashed after fuzzing, it means that you have a memory overflow or memory corruption problem. So still, the researchers find and run these fuzzing tools over mostly the open source programs. Okay, so for example, whenever a new open source program is published, your fuzzing tool starts fuzzing these open source programs, and if it discovers a memory corruption, okay, so as a let's say as a general rule, as a responsible and ethical hackers, we have to report it to the owners of these open source programs, or maintainers, let's say, not owners, or the maintainers of this open source program. So, but the cyber criminals don't do that, apparently, and they try to find exploitation ways of this memory corruption. So the memory corruption alone doesn't show any exploitation, by the way, okay? But memory corruption alone is, it's alone, it's sufficient to report as a disclosure. So just by looking at that, we can understand. Yes, the safe programming part is the most important part for this, in order to prevent these vulnerabilities. There was a movement, like at the time of writing, maybe generating of this code. Uh, so there was a movement called the memory corruption. In order to prevent the memory corruption, we need to move from memory safe programming languages like Rust, okay, or from C++ to Rust mostly, or Go. They are memory safe programming languages, and they have nearly the same performance, maybe not always for Go. Under some circumstances, Go could run as fast as C and C++, but Rust always said that it's going to run natively at these by these programming languages, let's say, speed. And so there was a movement from these memory unsafe programming languages to memory safe programming languages. But that also had some failures, like the Cloudflare's update, maybe 2 or 3 months ago. Cloudflare updated their core architecture from C++ to Rust in order to say that preventing memory corruptions in their services. But after running some time, maybe 2 days or 3 days, it crashed suddenly. Everything crashed suddenly. So they had to revert back to the old program. This was the most critical failure, but I believe they fixed whatever was missing, and they did it part by part. But they still have the moving of the code base from C++ to Rust. So that is uh, not only the correct algorithm implementation, okay, but also even though the algorithm is correct, the input would not be correct every time. So yes, this tells you about the machine language corresponds to algorithm, which is defined as software validation. Okay, so this is software validation. Formal validation. Formal validation means, formal here means in the form. Okay, whatever written in the form. So formal has two meanings. One meaning is in the form. Second meaning is official. In this case, it doesn't mean official. It means in the formal. So the software as defined in the form of rules. Okay. So formal validation means you write the rules first before writing the software. Okay. You write the rules, everything about the rules. Then you write the software. So someone else comes and reads these rules, and by checking these rules, it makes sure that the software you have written does nothing but these rules, which means that your software does everything by the rules, and it doesn't contain anything outside of these rules. So it's not as simple as straightforward task, by the way, to make. But there are ways to make these software formal validators. These are especially used in what industry? In, of course, aviation, okay, and in drones, because softwares can be developed everywhere. I mean, you can subcontract all the software to other parties in the world, but you want to make sure that this software doesn't contain anything other than whatever I have put as a rules. So the first thing is to develop these rules in a language that is implementation free. Only this is the mathematical language, by the way, of the software. So when you develop this mathematical language of the software, these are called the formal rules. So yes, the aviation industry, the drone industry, the war industry in general works like that. And you have to make sure that you have to check these formal rules against the developed software to see everything is implemented and nothing more than these rules has been implemented. This is also valid for hardware. There is also another unit called hardware validation. This is exactly the same. You develop the contents of this hardware design as a mathematical language, which is a separate one. Then you check the hardware against these rules, and you make sure that the hardware contains nothing but only everything that is defined in the rules. And the correct data interpretation actually gives us which these different programming languages have the interpretation of this data. So this is everything that boils down to here. That's why when I pass one data to another module, so this module should also interpret this data according to the rules of its own. That's why we say that data interpretation is important. And also, this brings us the correct use of memory. In the programming languages that actually does memory management manually, like C and C++, as always mentioned, these manual memory management programs actually could have issues with the dynamic memory allocation. By the way, the Apple's, for example, low-level programs are still written with Objective C, and the Objective C is still dependent on manual memory management. But we also see a tendency to move the Apple's core program implementation from Objective C to Swift, okay, which is the Apple's memory managed programming language that doesn't allow these kinds of corruptions inside. But still, when we go to the main cause of these buffer overflows, we still see the Objective C related code in the Apple's memory corruption problem. So that's a legacy defined. So that legacy could be overcome maybe in the future with more, let's say, powerful hardware, which can run everything in memory managed parts, and those memory managed parts can be separated from the other parts as well. Another thing is race conditions. So still we have seen a race condition in one of the most used softwares. I have to look it up. I don't remember the exact which one, but it was told that this race condition happened some time ago. I mean, it was found even maybe it was in 15 years. But I can say that the latest buffer overflow problem is about the telnet-D. Okay, this telnet-D, which was a part of Linux inetd, and if you are running seriously telnet-D, which you are not supposed to run, by the way, there's a buffer overflow in telnet-D that can be just triggered with a connection attempt and provide some specially crafted data, as they call it in this profession. with some specially crafted input, telnet D can be crashed with possible remote code execution with the context of course, telnet D, which is running as an inetd, but with the privileges of root switch. So even with that, it is possible to to have a telnet D like this. So but the race conditions, actually the conditions where two process tries to synchronize and tries to let's say prevent a corruption of a memory variable that want to write to the same memory location. So normally they should take their turn to update this memory location. The race conditions happen when one of the program tries to access this data while the other one is updating it, for example. Then it could either lead to deadlock, or it could lead to memory corruption of one of the modules, which may again lead to remote code execution. So these are mostly from the operating system execution. And also the environment variables are heavily used for memory overflow. Yes, this is another example of input. So for example, are the environment variables input? Would you think that environment variables are also the inputs for your programs? You should, because either you know or you don't know, these environment variables are used by most of the modules in your program, whether you know it or not, like the HTTPS, like any running interpreter, Python interpreter, PHP interpreter, or any scripting that is being tied with the one. So these environment variables could be abused as an input to your program or to another program, and it could be accessed. So again, these environment variables, let's say, checking is also used in computer security research, where these fuzzing is also done with these environment variables. So because it is also the sources of input, one of the sources of input. So this is an untrusted program input. Yes, it shows. I will not go into fully details of these vulnerabilities, but these vulnerabilities actually comes from these facts. For example, the path variable could be manipulated in order to, let's say, dynamically link of another program, like the LD library path. So because I mean, in Linux, one of the missing things is that it doesn't have program certificates or executable certificates that the Mac OS Windows has. So in Linux, you don't have, unless of course you define secure Linux architecture and require everything to have certificates and like the system protections and everything. It's not a regular thing that you do with Linux. Linux doesn't have certificate checking at the time of running of a program. So it could be easily an external library path could be injected into a program, and this could be exploited in order to access privilege. Okay, so why this is important? Because the program dependencies could be changed. You are actually injecting another or malicious library to the actual running program. That's how it starts with the privilege escalation. So in order to prevent privilege escalation, that's why the programs run with the least privilege. That's why also with this least privilege mindset, The programs asks you for access to camera, to microphone, the other things in the mobile programming, in the mobile part, which we will briefly talk about it later. And these are because of the least privilege principle. We want to limit everything to least privilege until the user agrees to elevate the privilege or escalate the privilege. And the root and administrative privileges are still one of the most important source of cybersecurity incidents. So usually some of the programs are left with root administrative privilege, and nobody cares to check whether everything is dependent on that. And one day they understand that everything was dependent on that because they were either their website were defaced or some of the personal PII data has been stolen from their servers, like the famous incidents about Yemek Sepeti or Hepsi Burada, or these kinds of things. They usually happen because of some left root administrative privileges of some programs. So by default, we assume that every program runs under their own privilege, but it doesn't happen like that. And another source is the system calls and standard library functions. These happens, programs make assumptions about these operations. So we rely on the standard library functions to perform these common operations. And these are also the source of how we have these problems. So the rules for preventing race conditions are usually, of course, done with the suitable synchronization mechanism, like locking of the program and the log files. And yes, usage of safe temporary files are also important when doing some, let's say, usually tooling part. So yes, I'm definitely going to share those secure software development input slides with you, because that's exactly where we were at. Because these safe temporary files usually happen at the maintenance and integration of the software. So these are the parts of software. You don't always treat software as only development of the software, but we develop the software as DevSecOps. Okay, so development, security, and the operations, the maintenance or the taking everything in line, should also have information about what they do. So you could be in development part, but you should prepare yourself for the security part and the operations part as well, sharing this information. So this means that the operations part is now affecting the software, secure software development, because some scripts, maintenance scripts, export, imports, and everything could be using temporary files, and they should be used in real temporary yeah file. I mean, it's just a reminder of what we should do with the DevSecOps. So other program integration means API security. So with the API security, we are actually not only dealing with the human generated input, but we are dealing with the machine generated input as well, okay, by integrating with the other programs. Another thing is that handling the safe program output. So it's not only just about the input, handling the safe input, but whatever you generate as the output should also be safe. That means we should apply the output filtering, output whatever the output encoding rules are, should be applied to our program output. Why this is important? Because our program output can also be vulnerable, so that somebody could be using us to reflect their input as our program output to inject. For example, most of the time XSS style injections happens because of that. somebody else is using our program output by controlling this program output from their input. So my program output is actually controlled by another program's input. So if I don't put a filter here for some specific cases where the program output really matters, then I am vulnerable. That's why the program output is also important, like the specifying of the character set, like specifying a certain string if it is in this output or not. These are the important ways. And yes, in general, the software secure software programming principles that we have talked about, and mostly the input style we talk about. So I'm going to stop here. We will come back in 10 minutes. Okay, let's start with buffer overflows. I'm going to also update. I'm updating these slides, but I might change just in a minute. But let's start with the history and how the mechanism. The buffer overflow is still a very common mechanism. It was first widely used by, of course, the first worm as well, Morris worm in 1988. And prevention techniques are known, but still the major concern. This is the legacy buggy code in widely deployed operating system and applications. So this is legacy, means that it is still legacy. I mean, we still discover buffer overflow after, let's say, 15 years of open source software development. And we cannot say right now the careless programming practice of the programmers, because right now it already passed the beyond the careless programming, but still it's a problem. So this buffer overflow is defined in NIST glossary as a condition at an interface under which more input can be placed into a buffer or data holding area than the capacity allocated, overwriting other information. Attackers exploit such condition to crash a system or to insert specially crafted code that allows them to gain control of the system. So what is being told here is this. In your program, you allocate a buffer and you expect the input to be less than or equal to this buffer. Okay. So let's say you have a buffer of this size and you have an input of this size maximum. So you expect it to fit in here. So how do you do it? You have a control over here. There's a control. So what if your control fails and this buffer, instead of this size, is, let's say, another arbitrary size, as it's called, try to be allocated here? Yeah, we will see what will happen. But in short, this excess part of this buffer is going to be written to some random locations in the memory, let's say. And the programming error when a process attempts to store the data beyond the limits of a fixed size buffer. That's the definition, as I have shown you. So it overrides the adjacent memory locations. So yeah, in the original aim of the buffer overflow was to overflow the adjacent memory locations, which the buffers were allocated adjacent to programming data as well. And because those locations could hold other program variables, parameters, or program controlled flow data, so buffer could be located on the stack, in the heap, or in the data section of the process. So a running process could have buffers in three different areas of the memory. First memory is the heap memory. Okay, so heap memory is the memory that is unorganized and let's say that's accessible, that keeps most of the buffers. But even the stack memory could hold buffers, okay, depending on the variable size and variable type. And of course, the data section in the process, which holds the data, the programming data at this one. All three portions of the program could hold this buffer. And what is the consequences of this corruption of the data program? First of all, corruption of the data program with unexpected transfer of control. So normally, what is the transfer of control? Your process, whatever you are running here, is currently in the control of the running program, okay, executable. How does it do this control? Whenever it executes an assembly functions, it has the return address of the next algorithm's executable low-level assembly code. It's going to pass this return address. So this return address will, whenever this function exits, it is going to jump to this return address and continue executing the program there. So in summary, this memory corruption actually changes the return address of the current running assembly code, and this return address contains my specially crafted buffers executable code that is going to take the control from the current running program to my program that I uploaded or that I created by sending this buffer. And my program is going to continue from here and do whatever it is going to do. So in other ordinary operations, and most of the operations, if you cannot overwrite this return address properly and put your program data into the new return address, then the program is going to crash only. Okay, it's going to only crash. It doesn't do anything. But since the memory is corrupted, the operating system is going to take control because no return address will be found. And since when the no return address is found, this program is going to signal the operating system as there is a violation, memory violation. Okay, so the operating system interrupts here and stops everything about this process and deletes all the process memory data while it's running, creating a core dump. Okay, so this is core dump. What is the core dump? Inside the core dump, it takes all the memory contents and writes into a file. Of course, if the core dumps are properly configured over that operating system. So in unsuccessful, let's say, buffer overflow attacks, the program is going to generate core dumps. That's also important. We observe core dumps while running the systems, but we don't usually we don't store these core dumps because sometimes these core dumps could overflow the operating system's file systems. So, but you can configure Linux to generate core dumps to specific locations, for example, whatever the program generates. So by examining these core dumps, the developers, if they have the source code of the program, and of course, if the debug symbols are enabled, otherwise it won't be possible to decrypt the variable names. If the debug symbols are enabled as well, then you can trace the source code with this program core dump and find whatever the actual memory representation of the program and find the actual error in the memory or in the program. So this execution of the code is chosen by the attacker. So in a very, let's say, simple representation, what we have is this is a buffer basic buffer overflow code. Why? Because let's say we have a character buffer, 8 bytes. Okay, then we try to compare this 8 bytes buffers into with the 8 bytes and say that yes, we this is successful or not. But what you will notice here is that when you do a get string here, okay, when you get the string, you see there is no limit, there is no number of bytes to read here. So if you ever provide more than 8 characters of bytes, this program is going to normally crash. Okay. So when we look at these basic buffer overflow stack values, the program data, first of all, is stored in adjacent memory locations. So these memory locations started from this, let's say from here, and these before this get s here, this is the content of the memory location. What does it symbolize? This contains the value of argv, the number of the contents of the arguments that this program has been invoked. Okay, like this one. So argv here, this is the running of this program. So if you start this program as buffer1, you didn't give any arguments. So this argument value is null right now. And the argc value is just next to this memory location. And this is the number of arguments. The only argument is the program name itself. So every argument, the argv value, argv value will be name of this program, not null. I'm correcting myself. This is buffer1 because every program has at least one argv value. This is the name of the program, and argc value would be 1. And then this is the return address of the current running function, and this is the old base pointer, whether the valid or not. Then we have the string here, like input, bad input. Okay, normally these memory locations are, normally, when I say normally, in the previous times, these memory locations were all adjacent to each other. So you see, this is this led to predictability of the memory locations and the return addresses. Okay. So yeah, we are of course starting from the easiest one, and but of course we have more of this when we just this, see, when we see the new buffer overflow attacks. So just I need a minute. I'm going to change these slides and come back. Just a second. So the stack buffer overflows. Okay, before that, yeah, I want to continue with this state of the art part. So the buffer overflow is turning from classic stack smashing to current the state of the art. So in a normal operation, these buffer overflow happens from the classic and heap and the globals overflow. So the modern exploitation in buffer overflow is done with rope, job, and data, which we will see. And today mitigations are usually happening with the memory safe shifting of the operations. Buffer overflow is still one of the broader memory safety in the native code. And modern attacks rarely stop at a single override. So they chain memory corruption, info leaks, and gadget reuse or the sandbox escape. These are all different concepts. What is this? This is, first of all, chain memory corruption with some leaks. This is one thing. So gadget reuse means that there is also the code that access to direct memory, but via some authorized usage. So you actually bypass that authorization and make this privileged code to work for you. And the sandbox means that these executables that are running have some limitations, that they cannot access some special parts of the memory that has privileged code or the kernel code. So that's called the sandboxing part. So these buffer overflows have to connect all of these vulnerabilities into single vulnerability or exploit in order to be successful. Okay, so the industry trend is shifting from mitigate every bug to reduce how much unsafe code we create. So what we say here is that we don't want to mitigate every bug, but we want to reduce all unsafe code. So this Google reported Android memory safety share was actually memory safety of Android was not trusted 76%. Now this untrusted part moved to 24%. That's good. I mean, that means only 24 percent of this Android code is now able to, has mitigations against buffer overflow. This means the code-based safety is working, at least for Google. So this is the direct result of usage safe code techniques, hardening and testing everywhere, but prioritize memory safety roadmaps for new and high risk code. So yes, the buffer overflow basics we have seen is that the variables, the adjacent variables, memory data pointers, or the control data can be overwritten. When a program is running in the memory, it organizes its codes as blocks in the memory. And these memory blocks needs to be adjacent because programs need to access them frequently. So if they are, let's say, they are kept apart, we cannot, let's say, the performance of the program will not be, let's say, as good as when they are in random locations. Of course, compared to the CPU power of the old times. But the modern CPUs have, or the modern architecture everywhere of locating these random variables, random memory locations of these programs by applying some very hardware accelerated techniques. So the outcome ranged from denial of service to authentication bypass, data correction, or arbitrary control transfer. So buffer overflow is not only about remote code execution, but again, it comes only from the denial of service, which means that your program is being crashed, is crashing by sending buffers. Or the authentication can be bypassed, or the data inside or the database can be corrupted, or the last one is you can control everything, remote code execution. So yes. So from the previous one where the Morris worm was created, okay, until the mitigation bypass era. So which means that these chains mix corruption, leaks, code reuse, sandbox escape, and privilege escalation. These are the new after 2020s. Okay, in this era, this is the current era that we are living. Now, only one buffer overflow is not enough to successfully exploit any system. Whatever we see in the current leaks of, I would say, Apple's iOS bugs, the Safari WebKit bugs, they are all uh, uh, more than at least three buffer overflows chained together. So again, what I was repeating is saying that this leak, this vulnerabilities was leaked from an official document that was used by governments. And that government, the developer was tied to another government. This government here has the access to Apple's source code. That was what I was telling. Because without access to source code of everything, it would be nearly impossible to determine all the buffer overflows inside the Apple. It cannot be done with static analysis. Okay, so whoever controls the Apple source code, it seems, have their advantage of. Apple is constantly trying to, from their perspective, control their developments and source code activities all the time, even with the internal controls, even with cyber espionage style of checks and everything. But they still cannot prevent, it seems, that their source code is still being analyzed against buffer overflow attacks. And possibly whoever making that analysis is working in the cybersecurity department of Apple. So at that time, it was only the executable stack and predictable addresses and the injected shell code. The buffer overflow was basically that. Okay, so let's say it is pre 2019. You could exploit a lot of things with this chain. So the typical goal to redirect the return address into attacker bytes. This is the classical buffer overflow. But this classical buffer overflow right now can never be executed on any modern CPU architecture, because all the modern CPU architecture has a randomized address control, and you cannot adjacently control the address or try to make these addresses predictable easily as before that. So the transition started with NX, STEP, and ASLR, the stack canaries. These are the techniques that, first of all, the hardware vendors used. So these are hardware vendors' technique in order to randomize the memory locations, creating privileged instructions to access those locations, and creating, again, something called stack canaries, so that the stack can only be executed by some, again, privileged methods. But the attackers try to find ways by return to libc, ROP, and JOP info leaks, which we will not go into the details of everything here. But the current trend is now the control flow plus the data-only attacks. This is one of the things. We just want to data-only attack. We just want to change the data that is stored somewhere. Because not always our final goal is to create remote code execution. But instead, if we control and change some of the data beyond the authorization of ours, we can have a constant, let's say, access to servers and the services that is given by these ones. And also the heap metadata abuse and the sandbox escape chains are current used, and these are mostly again related with the mobile operating system. So why mobile operating system? Because the mobile user information is always more valuable right now than the desktop operating system, because desktop operating system, maybe you have several ways to defend when with the desktop operating system, and also the server style of buffer overflow is also important. So there is no direct attack of buffer overflow for now on the it seems on the desktop operating systems, either on the server side on the cloud operating systems. These buffer overflow attacks occur, or the mobile operating systems. So the goal is usable primitive, not necessarily code injection. Okay, whatever that works, we want to use. We don't want to go all the way to these buffer overflow. So yeah, as shown, the unsafe code is with the bounce check. Okay, so this may seem very simple for now, the bounce check, but the boundary check is actually happens all C and C++ all the time. So still the static analysis, okay, static analysis, there are always bound checks and everything. That's how they find, by the way, still the buffer overflow codes. Always like this, but somehow the buffer overflow still happens even though everything was checked. So the frequent root causes is the missing object size knowledge at the call site. So that's one thing. So because of the dynamic, let's say, chaining of the programs, even though one program even though both of the programs has the checks, but the size of these checks, for example, may change. Okay, so the size check or the other program, depending program, even though it reads everything with the correct size, the input interpretation may be different depending on how this input is going to be interpreted. So the memory corruption still hurts most of the parsers, okay, image parsers, media fonts, and file formats. And most of the iOS-based or the Safari WebKit-based memory corruptions actually happens because of these images or even fonts. Okay, by providing unknown fonts to the program, these fonts to be loaded by the Safari WebKit. So if there is a corruption in reading the fonts, then it's going to create these problems. That's one of the things, font parsers, okay, file formats. The other one is privileged code kernel, drivers and hypervisors. This is mostly about the server part, which also network-facing services, protocol handlers, and proxies, like the HTTPS daemon, Apache daemon, Java-based Tomcats, and or Python-based applications. Other applications like Python also still vulnerable to these kinds of, at least from the buffer overflow or data corruption parts, not an executable code. But that's why buffer overflow may not be only aimed for executing a remote code execution. The current trend is changing. Instead of making remote code execution, we just want to change the data, access the data. Like even it could be your server's private keys. And embedded firmware limited hardening, that's also one thing. This is telling us that the embedded hardwares like iOS and Android is also under attack. And high risk when native code is both complex and reachable from the untrusted input, which means that the native code becomes complex every time when it's written in a memory unsafe language. And That's what it will happen. So the modern defense against these memory corruptions is that memory safe design techniques. One thing is that. The second thing is safer APIs, code review. Safer APIs means the input checking. So most of this input related problems happens when you read input from untrusted sources like APIs. Another thing, compiler and linker hardening. So of course, the compilers also add these canary stacks, as we have called, into the code base so that the stacks are not directly predictable when they are loaded into the memory, but the execution of the next stack pointers is dynamically updated in order to not to let's say predict. But those stack canaries, of course, they are the one of the things that the attackers was able to solve. I mean, it's again cat and mouse game every time. And runtime mitigations like NSX, ASLR, and sandboxing. These are limitations that are coming while you are executing the program. So every program in Android and Apple is running inside a sandbox, and that's why the buffer overflow exploits has to at least pass 3 layers, has to have 3 buffer overflows chained together. Otherwise, it will not be a successful exploit. It has to pass 1 layer, another layer, kernel layer, sandboxing layer, and the input layer. All the layers have to be successfully exploited. And these are runtime mitigations. And the hardware assistance actually comes from the design, hardware design. The fuzzing, sanitizers, and the crash triage, these are the post-mortem analysis of the buffer overflows. So by using the fuzzing on your, let's say, binary, you can find the memory. If there's a crash, you try to find how you can exploit this. And when you find it, as you say, this is definitely a buffer overflow crash. And mitigation raise attackers' cost. They do not make unsafe code equivalent to memory safe code. That's mitigation is only made for making the attacker's cost. Okay, it's not a defense against this. So the compiler linking and hardening is done with some compiler, let's say, flags when running this type of code. These actually, I mean, why these are important and what is the consequence of this? I just want to, I can just say that. So by enabling this, you are actually preventing some, let's say, flexibility in your program. But if you need that flexibility, then you have to change these compiler flags, which means that these compiler flags, some of the flags will not work for you because it's not your case. But there are limitations that's coming with that. So hardening reduces exploitability more than it reduces bug count. So hardening means you are not reducing the number of bugs, but you are reducing the number of exploits. Okay, bugs are still there. If there are bugs, they are there. You are just making the exploitation a little bit harder. That's all it does. The hardware, especially hardware backed mitigations and emerging techniques, actually comes from Intel AMD's CET. This is making all the buffer protections and privilege running separation of the kernel and the user data and the code together. It has an return address protection, indirect branches, and operating system and tool chain supports exist, which means that you can use these techniques if you chain them together with the compilers as well, which will create a safe hardware-backed mitigation of this code. ARM also has PAC and ARM has MP. These are the mobile operating system style of protection, we can say. I don't know what this theory is, but it is, I think, related again with the mobile development. Uh, so the hardware help is growing, but it is strongest when the whole stack, the compiler, OS, runtime, and app is built to use it. So that means every part of this game should be tied together. Okay, we still see exploits in Apple, uh, and we still see exploits in Android all the time. Of course, Windows and Mac OS exploits are definitely going forward, but the cost of these exploits and the value of these exploits are important. It's all about cost versus value. So it usually detects, starts with detection in the box, static code analysis. That's one thing. So with the help, that's why I was telling, with the help of LLMs and AI analyzers, let's say, these static analysis may lead to more, let's say, more robust programs. So I believe they are all being run, and those sanitizers like ASN is actually using. So it's excellent in testing, but too heavy for universal production use. What we call is that these ASN techniques, sanitizers, actually, when they are linked into running code, they prevent those buffer overflows by protecting the special buffers. Again, fuzzing is mostly used. Open OSS fuzz style, continuous fuzzing across large data sets. So the old mindset, write new code in unsafe languages, then rely on reviews, hardening, bug finding tools to keep up, and it resulted in persistent bug inflow. So, but the current best practice is to use memory safe language for new high risk code, and it contains legacy native code behind the narrow interfaces. So we rewrite the parsers, networks, everything, and keep hardening and fuzzing everywhere. So what is preventing for us to rewrite everything in memory safe language is, of course, the speed of the hardware and the limitation of the platform. But the shift is moving towards, like in the mobile operating system, where most of the part that are not directly related with the kernel, like the parsers, like the font parser in WebKit, could be rewritten in object instead of Objective C and Swift, so that the memory safety is done from the beginning. These type of, but when they write in Swift, for example, it could be something like it. I mean, it doesn't perform well, and it doesn't have the same performance as you do it in the native and memory managed, let's say, manual memory managed language. That's why we still cannot go out of it. So if C++ is unavoidable, which means some part of this still underlying operating system, underlying programs and everything is, if they still have to use, uh, then as a hardening recipe, there are some suggestions like using the CFlags, Fortify source, fstack protectors, strict flex analyzers, and everything. Like the LD flags and architecture specific flags, it is possible to compile these programs like this. But as said earlier, these are mostly only mitigations. They're not completely prevent everything. So of course, the safer input handling of again an example. So these are also mock example, but it just wants to give you the idea of what you get as the input and instead of that, handling every input with the size. That's what we want to say, the bounded input, sanitized new lines. I mean, still these are mock examples, not the real world examples, but I want to give you the idea of what this buffer overflow problem is and exploits are. That's how we do it. So just a second, let me turn back to here. Yes, these slides actually shows the classical buffer and stack overflow examples, which I will go over them briefly. These stack overflow is actually because of the frame pointer with the return address, where you change this frame pointer to another local stack pointer, and you have the control of the code. Okay, so this is like 10 years ago, without hardware protection and anything. 10 years ago, memory structure and architecture. Is it valid? I mean, even 10 years ago, the mitigations were there, but after in this year, this is only a historic example and historic model to understand what this buffer overflow means. You can only have the buffer overflow. I mean, this you cannot successfully exploit it, but you can have a core dump. I mean, the validity is saying that normally you shouldn't even have a core dump or a control core dump, but still, if you even cannot take the control of the program, you can still crash the program by using the bugs in the buffer overflow control. And this hardware mitigation and everything, software mitigation, is never ever going to prevent the buffer overflow with the denial of service style of attack. I mean, whatever you do, in one way or another, you are going to get this core dump. Definitely, if you use unsafe C code. But this core dump, depending on how it is handled, maybe most of the time it may be not important. It is just like something, hey, I couldn't use Safari, let me delete it and come back. And at that time, possibly a core dump occurred, and that core dump was deleted or that was prevented by another thing. So you didn't even see it. Okay. So these kinds of things always happen, but they do not create a security problem, at least from the security type, other than denial of service. If it happens constantly, of course, you have a denial of service. But it only happens one time. It's just a bug in the program. Yes, the at that time, the previous let's say times, main aim was to execute the shell code, okay, which was supplied by the attacker, and this shell code allows you to get a remote shell over the program. So there are still, by the way, when I say, I mean, can they still be exploited? They can be still exploited, but under with some strict conditions and with some several bugs chained together. So these actual buffer overflow and stack overflow programs allows you to execute the shell code, which means that like the bin, bash, or whatever the default shell value you want to execute, which is going to execute this shell code along with some parameters where you can have a reverse shell back to you, okay, connected back to you, so that you can log into this shell without any authentication and with the privilege of the root. Okay, that's why it was important in Stack Overflow once. So I have already talked about these buffer overflow defenses with the compile time and runtime defenses. Okay, and compile time defenses are done with the programming language flags by providing new, let's say, some special flags to the programming language so that you have a mitigation. It's not prevention. You only try to make the cost of attacking the program sometime. But the safe coding techniques are always important, we said before. These safe coding techniques either, I mean, the NSA, by the way, the US Internal Security already published the reports about safety codes from moving C to Rust some time ago, or like 3 or 4 years ago. And right now, yes, it works at some places, but also it introduces new bugs like denial of service bugs. I mean, that's what I was trying to say. Even though you have a complete memory safe program, the denial of service bugs it is avoidable. And I mean, your program is going to crash at some time. It matters whether this crash is exploitable or not. If it's not exploitable and if you're getting critical service with your program, then it means that you have a denial of service type of attack. So yeah, a lot of things has been rewritten from the beginning, like unsafe byte copy to safe byte copies. These have been analyzed with the static analysis tools, and right now, currently, all the previous code bases with historical code bases of every open source program, especially Linux, is right now is being investigated with LLMs for over possible buffer overflow problems. And from time to time, these discoveries are made, and those whoever make those discoveries publish papers about their new discoveries, and it is how that this profession is advanced. And these compile time defenses, I have also talked about it. At that time, the stack protection also was important. These stack protections means the random canary. Okay, canary in here is that the names and the locations of the variables, stack variables, are randomly generated. Okay, and these names and locations of these stack variables should be on different systems. So every system or every runtime, or whenever it's run, these memory locations should be randomly determined inside a given range. Okay, which should not be predicted beforehand, so that you shouldn't write in theory a program that expects the memory at the same adjacent location. At that time, this was called random canary. Okay, this special type of operation was called random canary, which was added by the compile time defenses. So the compiler adds some special instructions inside the code. So whenever a new variable is created, the name of the variable, internal name of the variable, and the internal memory organization of the variable was put into a random place in the memory, and depending on the other variables, all the variables were scattered around the memory. So that's called canary. And these stack shield and return address defender like RAD, they enabled these GCC extensions. So, I mean, most of the modern programs are done with that. These are the compile time. At the runtime, the executable address space protection was always there. These are the using of the virtual memory support to make some memory regions non-executable. This is still valid. Now, every update, every hardware and software update, Apple, for example, makes new usage of these non-executable memory. So with the latest iOS, for example, update, these regions of memory, non-executable memory, has been extended to some other kernel parts as well. That's why Apple still is advertising or suggesting to move to the latest operating system. And the issues are the support for executable stack code and special provisions are needed for them. And address space randomization, ASLR, ASR, as we have seen, is this is actually, instead of stack, all the stack heap and global data is completely randomized. The heap buffers address are randomized, and the location of the standard functions, everything randomized, so that they can always be located in the running program by using those random variables. And so the guard pages are to place guard pages between critical regions of memory. This is used for separating of the kernel functions between the user functions. Okay, the kernel or the privileged part of the memory is separated with random page memory, so that it's not easy to predict the next part of the privileged memory, we can say. That's why it's used. And the stack frames, replacement stack frames are used. They are actually used for non-executable stacks and randomization of the stack in the memory. Okay. Yeah, it's not so. Yeah, the system call, that's also an important. Any stack protection mechanism to detect modifications to the stack frame or return address by function exit code. This means that they try to prevent return to system call. Okay, that's where return to system part is always constantly randomized, so that you cannot create a remote code execution. But as I told you, right now the exploits are not about remote code execution. Even a simple denial of service is enough. Okay, so I want to stop here with saying that the buffer overflows are still valid and currently exploitable ones. But in the modern buffer overflow, it's not always the case that we want to create a remote code execution. The final, the ultimate goal of the buffer overflow is not remote code execution anymore, but it could be from a simple denial of service to data corruption